Chapter 30, Enzymes. Enzymes are extremely important because they're the biological catalysts of pretty much every single chemical reaction that occurs in the human body. The human body is too cold from a temperature perspective and too neutral from a pH perspective to really do chemistry on a fast enough scale to sustain life itself. And therefore, because the chemistry can't just happen on its own fast enough, it needs to be catalyzed. And that's where enzymes come in. Enzymes are molecules that catalyze chemical reactions and are absolutely essential to life because otherwise chemical reactions would not occur fast enough to keep a living cell alive. And so the typical biochemical reactions that occurs with enzymes are over 1 million times faster than they would be without the enzymes. So it's a huge accelerator. And like any catalyst, all it does is changes the pathway. So catalysis is kinetic, not thermodynamic. You start and finish at the same place. And this is kind of a typo. These two lines should be on top of each other because where you start and where you finish are the same. You don't change the starting point, you don't change the finishing point. So the thermodynamics don't actually change. What changes is the kinetics. A catalyst just gives you a much easier way to get from A to B, and because it's a lot easier, it happens a lot faster. And so with a catalyst, your activation energy is much, much lower than it would otherwise be. So imagine you could either climb this massive mountain to get to the other side, or if someone had dug a tunnel through it, you could just walk through the tunnel. Walking through a tunnel is easier than climbing a 20,000 foot mountain. And because it's easier, it'll happen a lot faster. And so that's the same thing as a catalyst. You don't change where you start, you don't change where you end, you just give it an easier way to get there. And so here we still start with sucrose and we still end with carbon dioxide, water, and energy. A catalyst just lets you get there a lot faster because it gives you an easier chemical pathway to follow. The apoenzyme is the protein part of the enzyme. The coenzyme is the non-protein part. A coenzyme is typically used for an organic molecule that's not part of the protein, like typically derived from a vitamin. Cofactor is a metal atom that might be there too. The holoenzyme is the functioning enzyme that consists of both the protein and the non-protein parts. And so everything comes together to form the full functioning holoenzyme, which is all of the parts combined. An activator, an inorganic component that the enzyme requires to function. It's similar to a coenzyme, but it's not called a coenzyme. It's typically called a cofactor. So cofactor is a metal ion here. And if you take biochemistry classes, they'll delve into a lot more of that because this is a super common motif in biology. You have this gigantic protein with another organic piece, and then maybe 1 or 2 atoms of a metal. But it's those metals that actually do the chemistry. For example, magnesium. This is key for organizing ATP. And so ATP has -4 charge. And so a lot of enzymes that utilize ATP will typically have 2 atoms of magnesium, 2+, so ions, to help neutralize those charge and to orientate the ATP. Zinc is used quite a bit in human enzymes. When water binds to zinc, that changes its acidity and it chemically behaves differently. And so a water bound to zinc has a different chemical profile than normal water, and that becomes very important for a lot of chemical reactions. And so a lot of times when you see zinc invoked, it's actually because water binds to the zinc, and now the water is much more active, and the water can do the chemistry that we're looking at. Specificity of enzymes. Some are more specific, some are less specific to what molecules they'll allow in. And if a molecule only reacts, or if an enzyme only reacts with one type of molecule, it's very strict. If an enzyme will react with lots of similar molecules, we call it promiscuous. It accepts a lot of different molecules. And then that actually is a science term that we use in biochemistry for these enzymes. That's useful with pharmaceuticals, like Abreva is a medicine for cold sores. And that only works because the thymidine kinase in a viral enzyme is a lot less specific than a human enzyme. And so the viral enzymes will uptake molecules that a human enzyme never would. And so it's a pretty useful antiviral medication because of that. All right, the substrate is the molecule that the enzyme acts on. So it's like the reactant. The enzyme does chemistry to the substrate. When we name enzymes, you typically describe the reaction that's being catalyzed, and they always end in ASE. So maltase, we are breaking apart maltose into two glucoses. Sucrase, we are breaking apart a sucrose into a glucose and a fructose. And that's sometimes called invertase. Lactase, we're breaking apart lactose into a glucose and a galactose. If someone is lactose intolerant, they're missing this enzyme, and therefore they can't break apart the lactose. And so it gets to the end of their colon where bacteria start eating it, and that causes the symptoms of lactose intolerance. If someone takes medication for it, it's typically a tablet of this enzyme, and so you're giving someone the enzyme necessary to break down the lactose. Anyone can oversaturate their body's ability to deal with lactose. And so sometimes when you see challenges where people drink like a gallon of milk in like an hour or something, you will mimic lactose intolerance. Because at that point, a person they've maxed out their capacity to break down lactose, and it's still getting through. And so it still will get to the colon, to those bacteria, who will then start consuming it, and a person will get the symptoms of lactose intolerance. All right, an enzyme that converts the amino acid serine into phosphoserine would be which of the following? That would be serine phosphatase. All right. So let's go over that again because that's not typically correct. Kinases add phosphates to things. So we would have a serine kinase. Kinases add phosphate groups to things. Phosphatases remove phosphates from things. And so, I see that they're going with your best guess, but it's still incorrect. Enzyme classifications. We have oxidoreductases. These enzymes catalyze oxidation and reduction. Transferases. We transfer one functional group from one place to another. Hydrolases. Enzymes that catalyze the hydrolysis of esters, carbohydrates, and proteins. Lyases, enzymes that catalyze the removal of groups. Isomerases, enzymes that catalyze the interconversion of stereoisomers and structural isomers. They isomerize things, and they take one molecule and make it into an isomer. And ligases, enzymes that catalyze the linking of two compounds by breaking a phosphate and hydride bond in ATP. So what can be deduced about the reaction catalyzed by the enzyme lysine decarboxylase? Well, the enzyme removes a carboxyl group from lysine. Lysine decarboxylase means you're ripping off a CO2 group from lysine. What class of enzyme would catalyze the following reaction? Well, here we have 3-phosphoglycerate to 2-phosphoglycerate. That's a different isomer. So this would be an isomerase because you're interconverting between two possible isomers. The reaction rate. This is defined as a change in concentration with time. How fast is a substrate being consumed? And enzymes catalyze biochemical reactions and increase the rates of these reactions. So calculate the overall rate of the appearance of product D with the following reaction data. So in 1 hour, we've gone from 0 to 0.5 molar. In another hour, we've gone up to 1.5 molar. In 3 hours, we're at 4.5 molar. And in 4 hours, we are at 6 molar. And so here we have a formula. The rate of appearance of D equals the total change in concentration of D over the total change in time. And basically every hour we are producing 1.5 molar of D. And again, this is not a great example here because it's not consistent. At 1 you don't have 1.5, you have 0.5. At 2 you don't have 3, you have 1.5, and then it jumps up. And so don't worry about that. This class didn't get into chemical kinetics, so we're not going to worry about those types of changes. For our tests, we'll use nice linear data that makes sense all the way through when you look at it. When you do kinetics, you'll see that the rate does change with the amount of substrate present, because the more of something there is, the faster it can react, and then as you start getting less and less of it, the reaction itself actually slows down. But we're not going to worry about that in this class, so don't worry about that. Transition state. This is the high energy state between the reactant and product. The transition state only exists at the very top of the activation energy curve. It's transient. It only exists momentarily. It's not something that can be captured or bottled or stored. It exists in a transient state. The activation energy is the energy necessary to get to the transition state to start the chemical reaction.